Okay, so let's make a very simple example that we can all go through, and I made it as simple as possible. So let's say you want to either take the umbrella or not take the umbrella. You have two things you can do, and there's some probability of rain, okay, somehow. Then what you would like to do is choose the action that maximizes your expected utility. Now, because we said before that every possible reward has its own utility, now our function u of utility is just depends on the reward we get. And the reward we get depends on whether or not it rains and whether or not we take the umbrella. So there are three possible rewards. One is you're dry and you're carrying the umbrella. So that's what happens. Whereas you're wet with an umbrella and then you're dry. You don't have an umbrella. Yeah. And each one of these has a different utility, and we just put it here. Yeah. 0, 0, and minus 10 and 1. So you hate being wet. You like not carrying an umbrella, but if you carry the umbrella, you're not wet anyway, so it doesn't matter. Okay, you could scale this up or down by adding some constants, but it doesn't make a difference. Okay. So now, why not calculate expected utility for this table? Yeah, should not be too difficult. Can we all do it? Yes. So what is the probability for rain? You have to fix a number, right? But before we do that, let's say what happens if we look at the worst case approach. Let's say that you're very conservative. Yeah. So you want to do what we call the maximum. So you want to take the action that in the worst case will give you the best reward or the best utility. That means you go through this table. For every action, you see what's the worst thing that can happen. So if you take the umbrella, then the worst thing that can happen is that, well, you get 0. If you don't take the umbrella, then the worst thing that can happen is you get a minus 10. Yeah. So the best thing you can do is take the umbrella, and then you guarantee to get a 0. Yeah. For the same problem, there is a minimax utility as well, where you say, well, let's be optimistic in some way, and let's say that we select an action, yeah, and then after we select an action, somebody else chooses the worst possible thing for us. And then also in this example, we see that you get a 0. If you select an action first, and then nature, so to speak, chooses whether or not it's going to rain, then if you select an action here, then it's minus 10. And if you select this action, it's 0. But if it's the other way around, let's say that we know whether or not it's going to rain, and you select the action later, then, well, it's slightly different. Okay. So let's think about it like this. So this would be the game where Thor, let's call it, chooses the rain first, and then after we see Thor choose, select whether or not we want to take the umbrella. And this is the utility of the game if we select whether or not we want to take the umbrella first, and then Thor chooses whether or not to rain us. Yeah. But the problem with this, in this case, they have the same value, but in general they must have a different value. And the problem with this formulation is that you don't really want to be either minimax or maximum. You don't want to be either very pessimistic or very optimistic. You would like to have some way of expressing your uncertainty more exactly. So we use probabilities here. We can say that we have, let's say, 0.2 probability for rain. Yeah? And in which case, if we take the umbrella, then probability 0.2 have a minus 1, and with probability of 0.8 we have a utility of 1. So we have 0.8 minus 0.2, which gives us actually 0.8 here, so that's kind of wrong. That's fine. And if we actually take the umbrella, then no matter what happens, we have expected utility of 0. Okay? So that should be a very simple example. Okay? So here I just want to multiply this by 0.2 and this one by 0.8, and you add them, and you get this. Okay? Now this is one of the problems where what happens doesn't depend on whether or not we take a specific action. And this is very common in statistical problems where there is some underlying model of the world, and this model is true or not independent of what we actually do. Yeah. this is not like these artificial intelligence problems where we're driving a car and what happens depends on what you do. This is something where there is something unknown, and then you are uncertain about this unknown thing, but then what you get only depends on your action and this unknown thing, but your actions don't change the underlying reality of the world. Okay? So this is a setting where the actions you take have no effect on the things that you don't know about. And there is something called the Bayesian utility, for which you maximize expected utility. Okay, so there is something that we would like you to work as an exercise for next week, and this is basically the meteorologist problem we sketched today. Here you have a bunch of meteor stations, and they are giving predictions for the rain. And now assume you have this utility matrix we had before, where every day you decide whether or not to take the umbrella. Okay? Now you would like to make the decision that maximizes expected utility. Yeah? And the idea here is to use the marginal predictions of the radio stations, of the meteorological stations, to calculate the probability of rain, and then for every day choose whether or not you can take the umbrella. Yeah. And this should be pretty simple, and you will get some more hints about how you can do it when we go through other decision problems. But this is your exercise for 2 weeks' time. Yeah. It's not part of the project work, but if you complete it, then you will be on a good track to actually doing the project work. Yeah. So it's a warm-up exercise. Okay. So the first thing is to calculate the belief about the quality of every meteorologist every day. So this is just the belief that we calculated before. Then you can calculate the probability of rain for every day by just averaging the probabilities of rain for every meteorologist and multiplying with your belief about which one is the right meteorologist. And then the question is, how do you decide whether or not to take the umbrella? Yeah? So again, given this utility matrix, just calculate the optimal decision. Yeah. And you should make the problem general enough so that you can actually plug in any U matrix that you like. Okay. Now, these are some kinds of problems that called hypothesis testing problems, where you have a pair of hypotheses that are different, and you would like to decide which one is the correct one. Okay. So, for example, you can say Coca-Cola causes cancer or doesn't cause cancer, for example. Okay. But usually, to do that, you have to specify what it means that something causes cancer or not cause cancer. And to make the optimal decision, you also have to specify some utility matrix for making the correct choice. Okay? So in this simple case, you would say that the utility is 1 when you correctly guess something and 0 when you don't correctly guess the model. But in some cases, it might not be. So for example, if lots of people are taking Coca-Cola and then if there is a risk for cancer and you don't guess it, then it has a very high cost. So it's more important to guess that there is a risk for drinking Coca-Cola than if you don't guess it correctly and there is a risk, okay? And there is no risk. So if you go back to the medium example, let's say John is a medium, and let's say now I would like to bet. Yeah? He plays it a few times and he guesses 4 times correctly, and now he says, well, let's bet. Yeah. Whether or not I will be able to guess correctly the next time. Now, in this particular scenario, you would be inclined to accept or to reject the bet based on how likely you think he's going to guess. Yeah. So if he says, I will give you €1 if I don't guess, and you will give me €1 if I do guess, then that might be a fair bet if you think he's not really a medium. Okay? But if you think he is a medium, then it's not a good bet for you. Okay? So you can then calculate the expected utility of doing this decision. And basically, if you have this even bet, then it's exactly equal to the probability. To where you take action 1, take accept, if you really think it's more likely that he's not a medium compared to when he is a medium. Okay? So whether or not you actually bet or not with him doesn't affect his being a medium or not in this scenario. Okay. Now this is nice and simple in the scenario of, let's say, a medium where you have a specific model for being a medium and a very specific model for not being a medium. But it's a bit complicated when you're dealing with cases where you don't really have an alternative model. Let's say, okay, if this person is not a medium, then I'm not just guess at random. Okay? So that's your model in use error. But then you say, well, what if he's a medium? What is the right model for a medium? Does he predict 60% correct of the time, 70%? Maybe he can predict 3 times. He gets tired, maybe, I don't know, maybe there's something, okay? So you have to have some alternative model normally, but there is none, okay? So if there is no other model, then what we call, there is this problem called null hypothesis testing. Well, there is some model, but can specify, and then you would like to see whether the data comes from this model or something else. But there is something else is not really defined. That's actually a problem because it creates many problems in reproducibility. Okay, so here we have, for the medium, we say that if you are not a medium, then you're 50% correct. Okay, and we would like to design some policy, some way of saying accept or reject. Okay, that's your policy, given the data. Okay. The data is X is how many times he correctly guessed, for example, or the series of guesses he did. So now the only thing we can do, how to design this policy? Yeah? We have no way of designing this policy other than measuring its performance when the model mu0 is true, because we have nothing else to look at. Okay? We just have a way of measuring the performance of this policy when we know that he's not a medium. We don't really know what will happen in our policy if it's actually a medium. Okay? But for actually doing that, it's not difficult because what we're going to do is this, right? So let's say we have some performance measure for the policy. Yeah, let's say we have some performance measure, and this is our policy, pi given x. Okay? And you have some performance measure. And the performance measure is the utility, yeah? Okay, and there's also the model where it's the correct model or not, right? So let's say for the case where the model is correct, there is this performance metric. And we can also have a probability of observing data x. Okay, so if we don't know the data, so before we see any data, we design our policy so that when we see the data, we have a good performance for our policy. And this is basically the expected performance of our policy under this model. Okay, without seeing any data, we say, well, some people will come every day and they will say, I'm a medium, okay, and I want to have a policy that has a good performance for predicting, for correctly deciding if they are a medium or not. But I have no idea what a real medium is, so I'm just going to base my policy decision or how to design the policy on what I know about people that are not mediums. Okay? And that's basically null hypothesis testing. And this is what you see a lot in scientific literature. And there are specific things that you see about it. But what you usually do is you say, select a policy that maximizes this, okay? In some way. I want to have some policy that kind of maximizes this. Or has some constraint, satisfies some constraint about this. And I will tell you a little bit more about it, not because it's central to the course, but because the course talks about the reproducibility a lot. And one of the things that people use for reproducibility, for measuring it anyways, null hypothesis testing and p-values. So even though I'm not fond of them, they're used a lot, so I kind of have to explain it. Okay? So let's see. Has anybody here heard of p-values before, by the way? Yes. Have you ever used them? Great. Okay. So what is a null statistical test? Well, let's say we specifically care about this metric of how good our policy is. Okay? We want our policy to only reject, or to say it's not this model, a small percent of the time when that model is true. Okay, that's what's called a fixed error rate for our policy. So specifically, let's say you have some way of summarizing the data. This is called the statistic F. Okay? In this particular case of coin throws, it can be the number of times that the person guessed out of the total. Yeah? So it will be two numbers. Number of correct guesses and number of incorrect guesses. Okay? But we would like to summarize this data instead in just one number. Okay? And we would like to summarize in such a way that the probability of this statistic being smaller than the value delta is equal to delta. Yeah? This is called a p-statistic because it has the property that it's only wrong delta percent of the time. Okay? So the interesting thing about it is that what you do is you design your statistic so that when this model is true, the model of not being a medium is true, then for any delta you choose, the probability that your statistic value is below delta is exactly delta. Yeah? So that means that when the model is correct and the person is not a medium, they will be always incorrectly guessing that he is not a medium, that he is a medium, sorry, delta percent of the time, a delta proportion of the time. Yeah? But if you look at this definition, this is exactly the same definition as the uniform distribution. So the statistic F, which is what is the p-value that is reported in a lot of experiments, when the null hypothesis is true, has a uniform distribution. This means that if you run an experiment and see a particular p-value, let's say 0.1, then the probability that this 0.1 is the same as 0.9. So in that sense, the value of what you see of the statistic itself is completely uninformative, but it's a useful intermediate number that you can use to construct a policy that has a specific performance. So this is how you're using it. So normally when people design this idea in the first place, they said, well, we want a simple way to describe a policy for rejecting this null hypothesis with a specific number of mistakes that you can make, and this number is called the p-value. But you were not supposed to actually report the p-value, you're supposed to just accept or reject. And then the performance of your policy basically is fixed to be this delta. But the specific value that you get is not informative at all. Basically. Now there are some various issues with p-values. They only measure the quality of it on the data itself, right? If you have the wrong model, then of course this is not robust. They ignore effect sizes, so they just tell you how close you are to this null model, which is there's no effect. But if you want to measure small effects, then it doesn't work. There's no prior information involved, so if you have some information, let's say you think that you are more likely to be a medium than somebody else, and you cannot add that in, they don't actually consider the probability of making an error, so the thing that you see as a p-value is just this uniform distribution when the null model is true. So it's not really the probability of having made an error, it's just some technical thing that appears there. And because of the design of these tests, the actual error probability of rejecting the null hypothesis when it's true is always the same. Doesn't matter how much data you have. Yeah? Okay, so how does it work for the medium? Let's say we'll design a very simple test, okay? So that you see how it works. We have the Bernoulli model. 50% of the time you are correct, 50% you are incorrect. There is nothing else. Now we can plot the CDF, which is basically the probability that you have lower than a specific number of successes. Yeah. So by looking at the CDF, you can just pick any value here. Let's say here at 0.2, and then the probability that you have smaller than this many successes after 100 trials is 0.2. So if you make a test that rejects the null hypothesis when this is true, then this test will have an error rate of 0.2. Yeah? So it will be significant. So you can select any value you like 0.05, 0.01, and for any value you select, it gives you a specific threshold for the number of successes you need to have in order to be to reject the null hypothesis. That is completely random. Yeah? We'll put the other way around. Yeah? For any given threshold that you select, there is a given probability, or for any given probability that you select, there is a given number of successes that you need to have in order to say, okay, it's not random. for its round. Okay? So this is the CDF cumulative density function, basically. So it always has to go to 1. And this is the inverse version of that, so it just rotated 90 degrees. Yeah. So maybe it's easier for you to see, but it's the same thing. So for any significance value that you want, let's say 0.2, find the right threshold, which is, let's say here 45 or something. And then after you have set this threshold, then you run your experiment a number of times and you see what you get. Now, what's the problem with this? How do you do this in practice, right? Well, you can just do it with this function, the binomial CDF function. Yeah? And this basically is a statistic that we wanted, and it's going to be exactly smaller than delta, exactly delta proportion of the time. But it is not the probability of observing the data under the model. It's a different thing. Yeah? Because this is the 1 minus the binomial cumulative density function. It's not the probability of x. It's a completely different thing. It's also the probability of the model given the data. Okay? So if you write it down, basically, okay. So it's not going to be, it's not the probability of data, and also it's not the probability of the model given the data. Yeah. It just 1 minus the binomial CDF. Okay, and the distribution of f of x is uniform when this is true. So f of x, given that this model is true, comes from the uniform distribution. Okay, 1, 0, 1. Right. So let us do a simple exercise here. Okay. We have already done this once before, so let's continue doing it. But why don't you each throw a coin 8 times and predict the outcome? So I'm going to write some numbers here, okay? And you write 0 and 0, 1 as many times as you like. Okay, so I have written 8 numbers, 0 and 1. You can also write something. And then after you have written something, I will call the numbers and you write down how many successes you have. Okay? So first 0, 1, 0, 1, 0, 1, 1, 1. So it's completely random, as you can see. So these are the numbers I have generated, and please tell me how many successes you have, one by one, if you like. Go ahead. How many successes do you get? 5. Okay. How many successes do you have? You haven't got any successes. 3. You haven't done. Why not? 4. Okay. You got 4. It's pretty good, right? So you have some successes. So if you select what people are using normally as a threshold, like 0.05, you see that there is a rejection threshold for the proportion of the number of times you get things correct, and this decreases over the number of trials you have. So you have just 8 trials here. Yeah. So here you have like 87.75 success rate, right? And what is 0.7? I don't remember. Let's see. I guess it's something like 6, right? Yeah, it's 7. So if you had 7, if someone had 7 successes, then they were declared to be a medium. We didn't have 7, we had 5. But if we were like 100 people, then at least one of us or two would have done it, right? So what you actually get, if people, let's say, you have to now, here I'm doing like 1,000 experiments and throwing a coin for 1,000 trials as well, and I'm averaging the number of times that you actually rejected the null hypothesis when it was true. Okay? So you see that this doesn't change over time. It's always 0.05. Now, if the data actually came from a distribution slightly away from 0.5, 0.55, see that this increases over time. Yeah? Because the more data you have, the more sure you are. Of course, if it was closer to 0.5, then it would be going lower. Yeah? But the problem is, the main problem here is that you don't have this effect where you reject more the null hypothesis, or less, sorry, when it's true, as the data increases, because of the way this is designed. So to do it properly, you have to have a way of recreating the test so you put the right value there in your delta, but that's not really easy, right? So you have to know exactly how the algorithm works and how to do it. So it's not trivial. Okay, that's one problem. Okay. What's the other thing? The other thing we want high power. Yeah. When the null is false, we really want to reject it, right? So here we see that we reject the 0.55, but maybe not 0.4, or maybe if there was some completely different model was true, then we would not be able to reject at all. Okay. Now, the power depends on what we consider as an alternative. So it's not something clearly defined. But if say you want to maximize power with respect to the 0.55 model, then you can do that if you want. Yeah. And the false discovery rate, so how many times we think we found something that is not true, depends on our priori assumption about whether it might be true. So how likely is that some randomly chosen person will be a medium? Yeah. If you don't have that, then you aren't able to do it. Okay. So that's why I would normally suggest the Bayesian version of the test. And this basically says, now you don't have just one model, you have two models. There is no way you can do it with one model. You have to have two models. So one model is clear. It's a model where everything is random. Yeah? But what should the other model be? Let's say for simplicity that the other model says that the prediction rate of the other person is anywhere between 0 and 1. So you really like a very stupid medium, like the other way around. So you always predict wrong. Right? That's fine. That's also possible. Okay? But we don't know this value, so it could be anywhere from between 0 and 1. And this, if you remember, corresponds to the example we showed with the beta distribution. So we can model this as saying that the alternative model is basically the average model of every possible Bernoulli parameter between 0 and 1. And this is very easy to compute because basically the beta distribution is closed form and everything that you can do there is very simple. So this is the same posterior distribution that we saw in every other occasion. We have two models, the probability of one model versus the other. Okay, mu0 and mu1 are the two models. The only difference is here that mu0 is specified as a single point model, the probability always being Bernoulli half. And the other model, the alternative model, is any possible Bernoulli model between 0 and 1. And we can do this in closed form, so it's not really a problem. But what is interesting is the result that you see. So in our particular case, let's say you use the utility where you have 1 when you guess correctly and 0 when you guess incorrectly. So for the same example as before, you can see that the posterior probability of the null hypothesis goes to 1 when the null is true, and goes to 0 when it's not true. Okay? And here it's the same distribution as before. So that means that we are more or less correctly selecting the right thing most of the time. Yeah. Now, if I compare the two tests, the null hypothesis test and the Bayesian test, then you see here that when your data increases, then the probability of falsely rejecting goes to 0 for the Bayesian test. Yeah. Because by design, it just has to go to 0. For the other one, by design, it is constant. This is normal. There's not a problem with that. It's fine. Yeah. You have similar performance on the rejection of the null hypothesis when the null hypothesis is not true. It's also fine. And slightly worse performance, but that's okay. I mean, there's a trade-off. And the nice thing about the Bayesian approach, though, is not the specific performance, but you can always design a test that has the performance you want, because this is just a simple decision rule for the Bayesian test. The only interesting thing is that if you use the Bayesian idea, then you are very clear about what are your assumptions. What is the one model and what is the alternative model? What's my utility? What type of errors do I care about? What's my prior belief about what's the right model? So you can put all there in the model directly and say, this is what I believe, and this is the conclusion. And what's the nice thing about that in the end? When somebody takes your result, your posterior, they can use it plug in the new data. They don't have to not do a new experiment from scratch, right? if you have this null hypothesis test, it gives you a p-value, there's nothing you can do with it, basically. It's not enough. So there was this movement in statistics for people to use more Bayesian tests. It hasn't succeeded very much. But in theory, if you use posterior distributions and you publish them in your code and everything, then you'd still be able to use them to do follow-up experiments and refine the posterior distributions. Okay, so there's far too much for me to go through, right, here. But there are some very, very nice high-level articles in Nature Methods that talk about all those things. Importance of being uncertain, error bars, p-values, they're very, very nice, and they are kind of a couple of pages each. So I would really like you to read them, even if we don't use them very much in the course, because we will not do science so much. But if we're doing real science, then these are things that you should know about. And they are going over many of the things that we went through here. Okay. Good. Now, I will finish with classification problems as a slightly different type of decision problem. And tomorrow we'll go through more of these problems with some examples. Okay? But let's see. So normally when you do classification, right, what you have is you observe some features. And oh wait, maybe I should stop here. Do you have anything you want to ask about this p-value stuff? Oh, okay. Just wondering. So a slightly more complicated decision problem analysis classification. Okay? I say slightly more complicated because what you do in classification doesn't really affect what's happening. So you just see some data and you do some classification decisions normally. So you have some features, okay, that you observe at any point in time in T. There is some label YT that you observe, and then you make a decision. And normally in standard classification problems, the decision is to assign a specific label from the one that exists. But there are extensions of this problem where you must say, I don't know, or call somebody to tell me what the label is, yeah, or something like that. So you might have this in, for example, intrusion detection or fraud systems where the system will not actually say it's fraud and block your account and say, well, notify some person to call you and tell you, is this transaction okay? Yeah. So it's not like everything is classification is black and white. Yeah. So basically, as before, we have this decision rule or policy that takes an observation xt and assigns some decision to it. Okay. As I said before, in the standard classification problem, you basically have the same number of actions as labels, and your utility is just 1 if you correctly guess the label and 0 otherwise. So that's very simple. Okay. Yeah, this one to work out now, right? If you have some model P, somebody gives us a model. So for every xt that we see, there's a non-probability for the yt and some utility function, then what is the optimal decision to make? So how do we write this? Yeah? What do you think? What we want to maximize first of all? We should formulate this as a maximization problem sometime. Yeah? So we want to maximize some expected utility. Yeah, that was our main shtick here. Okay. And what do we see? So it's conditional on something else. So what do we see? What are we conditioning on? So observe some features, right? And we want to guess the label, right? So we condition on the features, right? Or not? Yeah. Okay, and then we condition on what else? So what does the utility depend on? It's a function of two things, right? Our action, our classification decision, right? And the label, right? Okay. And we see, what do we see? Do we see the label? No, right? Okay. The action, do we see the action? We choose it, right? Yeah. So we choose the action, okay? So we want to maximize this guy. And we have the model, let's put it there. Okay? So this is expectation, right? So how do we write the expectation? over the thing that we don't know that is random is the label y, right? Yeah? Okay. So now, what can we write here? Probability, right? Under the model, what? Of the y, right? Okay. We don't know what it is, so that's our all possible ones. And what else do we have? And this, right? And these are action as well, right? But the label shouldn't depend on our action, just there. Okay. So just remove that. Okay. Otherwise it should be there. But the label is already there, we don't have anything to do with it. Okay, and then there's the utility that we defined already, right? Okay, so that's our rule for maximizing. So if you had a model that tells the probability of every y, then and you have the utility function for different types of mistakes and correct decisions, then this is how you select the action. Okay. Now, what's the problem here? Well, we don't have this model normally. Okay. So this is what we have here. And yeah, so when the utility function is 1, right, is the identity. Is there something somewhere? Do you see a blackboard whiteboard thing somewhere? Ah, yeah, thanks. Okay, so when this is the identity function, right? So identity function x is 1 if x is 1. Okay. 1 if x is 2. 0 otherwise. So then for the identity function, then basically you have some y, probability y equal y, then x t times, well, a t equal y. Okay, so for every y that's not equal to 80, this is 0, so then it just becomes this. Okay, so that means you should just select the action mode to maximize the probability. And so this basically drops out the classical classification problem, but we don't have the model. Okay, and since we don't have the model, what do? Well, there is the Bayesian idea again. You don't have to always stick with the Bayesian idea. Tomorrow we'll go to something slightly different, but I will finish with that today again. So we have all these possible models, and every model tells us a different probability for the class labels given the features for everything in our dataset. So we have some training data from 1 to capital T. It's all pairs that we know the labels of, and then given this and the stuff models and the prior distribution, we'd like to compute the posterior distribution. Now, the posterior distribution computation is not very difficult. I specifically mentioned this as a way to do it. But again, it doesn't seem right because what you have normally is not this form, right? For the posterior distribution. You have all the data inside this, not conditional or something else. Yeah. So I will make a small parenthesis and say why it's like you can write like this. Okay, so a small parenthesis where we say that you can write, okay, we have this thing, right? Let's write all the data like this. So this is all the data. I kind of summarize it in just two things, okay? So normally you have the data, okay? And this is just P of mu, right? Of the data, given this, and then you sum over all the other modes. is fine. Now what I'm saying is that P mu of D is just P mu of x and y, and then we know that this is just that. Okay, just by definition of the joint distribution. Okay, so the conditional times this thing is always flat. There's no problem with that. Okay, so that seems to be okay, almost. But here we have a P m mu prime, right? So if P mu x is equal to P mu prime x for all these, then you can rewrite the above just in terms of the y's given the x's, okay? Because everything cancels out. Okay, and this is pretty important here because we only require our models to specify, to say that implicitly we specify our models to have the same probability for every observation in the x's in the futures, but we don't actually have to specify what this is. Yeah, it just cancels out. So we just say all our models assume the same distribution over the x's. We don't care what they assume, as long as it's the same. Yeah? And that means that we only have to specify in our model the probability of the y given the x, which is usually much simpler than specifying the distribution over the x's, which is complicated. Because the labels are very simple, binary thing, for example, and the x's, the relationship between them might be very complicated. And we really want to ignore that most of the time. Yeah? So that's one way you can think about it. Yeah? It's not the only way. Okay. So now another thing we want to do here is, well, we don't have a time series, so we assume that normally the data is independently drawn. So if it's so, then we can rewrite this like that as a product. Okay. Now we'll go to the Bayes rule for doing that. I think it's pretty simple. What you want to do, like here, right, is to maximize expected utility. Now there's a difference, there's only one difference. The difference is that here we have a specific model, and here we don't. We just average over many models. So we sum over all the models and multiply by the probabilities. Okay, but it's the same thing, nothing's changing. And the nice thing about it is that if you look at this term here, this is basically what is called a posterior marginal model, like the model average prediction. Yeah. So it's like you have a new model, which is the average of all these models, and you can use that one as a replacement. And your decision rule is exactly the same as here. You don't have to do anything very different. So your decision rule is pretty simple. You have distribution over models. You have a way of assigning probabilities to classes for every model. Just average all of them, and for every choice you make, there is a probability for the label given all the models. So you just calculate the maximum. Okay? So if you can do that, this calculation, which is not always trivial, then actually making the optimal choice is pretty simple. Okay? And tomorrow we will go on to what you'll do in cases where this is not trivial to do. Okay? There are approaches called maximum likelihood, maximum approximate, maximum posterior, and they are more related to things like neural networks and stuff. So we'll talk a little bit about that tomorrow. Okay? And this will end the introductory lectures to machine learning related topics. Okay. We'll have some time for more questions if you want. But tomorrow we'll go through an example of this. Oh, by the way, there are more stuff in the decision theory source thing in the repository. There are many examples you can play with, doing things I have no time to go through. If you have more time than I have.